Hey, my friend, if your mind is full and the day feels heavy, you're in the right place. Here we explore the universe slowly, softly, in a way that helps you unwind and drift towards sleep. So get comfortable and let the stars take over from here. Chapter 1. What we call matter under normal conditions. When astrophysicists speak about extreme matter, crushed into white dwarfs and neutron stars, they are always comparing it to something quieter. To understand why those stellar remnants are so strange, we first need a clear picture of what we call ordinary matter, the kind that makes up a room, a planet, and the familiar parts of a star. In modern cosmology, this everyday substance is usually called normal or baryonic matter. It is built from protons and neutrons bound together in atomic nuclei, with electrons forming a surrounding cloud. This atomic material forms everything we can see directly, from dust grains to galaxies, even though on a cosmic scale it represents only a small fraction of all the matter that exists. At the atomic level, ordinary matter has a layered structure. Each atom has a tiny, dense nucleus made of baryons, usually protons and neutrons, and a much larger region where electrons are found. The nucleus carries almost all the mass, while the electrons are responsible for chemistry, how atoms bond, how they emit and absorb light, and how they join into molecules. Protons and neutrons are not fundamental. They are composite particles made of quarks bound by the strong nuclear force. But under normal conditions, those quarks are permanently confined. We never see isolated quarks in daily life. We see only the composite particles they form. Most of the matter you interact with belongs to one of a few familiar states. In a solid, atoms or molecules occupy relatively fixed positions, vibrating but not flowing past one another. In a liquid, they are still close together but can slide and rearrange. In a gas, they are far apart, moving freely and filling whatever spaces is available. When energy is high enough to strip electrons from nuclei, matter becomes a plasma, a mixture of ions and free electrons. Plasmas are less common in daily life but very common in astrophysics. Stars are immense spheres of plasma, and much of the interstellar medium also exists in ionized form. Density is a helpful way to imagine what counts as normal conditions. It tells us how much mass is packed into a given volume. Liquid water at standard conditions has a density of about 1 gram per cubic centimeter, or equivalently, about 1,000 kilograms per cubic meter. Rock is usually several times denser than water. Metals can be denser still, and air is far less dense. Yet even the densest materials you are likely to hold in your hand are remarkably dilute compared with the matter inside a white dwarf or neutron star. Planetary cores, compressed by immense gravity, are dense by everyday standards, but still far from the densities where the nature of matter itself changes. Quantum mechanics gives ordinary matter its subtle internal rules. Electrons do not orbit the nucleus like tiny planets. Instead, they occupy quantum states described by orbitals, fuzzy regions where the probability of finding an electron is high. The energies and shapes of these orbitals explain the periodic table and the pattern of chemical bonds. One principle in particular, the Pauli exclusion principle, states that no two electrons in the same system can occupy exactly the same quantum state. This restriction is one of the reasons atoms have size and why ordinary matter resists being squeezed into an arbitrarily small volume. The electrons in neighboring atoms refuse to share the same quantum states, so as atoms are pushed together, they push back. Under normal pressures and temperatures, the macroscopic properties of matter are dominated by electromagnetic forces, thermal motion, and these quantum rules. When you press your hand against a table, the table resists not because something solid and impenetrable lies under the surface, but because the electrons in the atoms of your skin and the electrons in the atoms of the table are being forced into close proximity. Electromagnetic repulsion between like charges, combined with the exclusion principle, prevents those electrons from sharing the same space. The result is a restoring force that you feel as rigidity. Thermal motion works in the opposite direction, tending to spread particles out. The balance between these effects explains why solids keep their shape, liquids flow but are hard to compress, and gases expand to fill a container. At the scale of a human body, gravity is weak compared with these local forces. It keeps your feet on the floor, but it does not strongly compress the matter that makes up your bones and tissues. For the Earth as a whole, gravity is stronger, and it does squeeze the interior into a more compact state than the surface rocks. Yet even there, the fundamental identity of atoms remains unchanged. The electrons are still arranged in orbitals around nuclei, and the material, though under great pressure, behaves like an ordinary solid or liquid. When astrophysicists refer to matter as being under normal conditions, they usually mean that it can still be described in terms of atoms and ions in this familiar sense. This includes the outer layers of stars, the gas between stars, and the material that makes up planets and moons. In these environments, we can use the same physical models that describe laboratory gases and plasmas on Earth. Classical thermodynamics, statistical mechanics, and well-tested atomic physics are enough to predict how the material will behave. Temperatures may be extremely high and densities large by human standards, but so long as electrons remain associated with specific nuclei and atoms do not overlap so severely that their quantum states merge, the matter is not yet in an extreme regime. The behavior of normal matter under these conditions sets the stage for almost everything in astrophysics. The way interstellar gas cools, how molecular clouds collapse, and how stars are born all depend on how ordinary baryonic matter radiates energy, interacts with light, and conducts heat. Atoms can absorb photons at specific energies when electrons jump to higher states and emit photons when they fall back down. These processes create the spectral lines astronomers use to determine the composition and temperature of stars and nebulae. The same atomic physics that explains a glow in a laboratory gas explains why certain colors appear in the shining gas of a distant emission nebula. On cosmic scales, normal matter is only one player among several. Observations of galaxy rotation, gravitational lensing, and the pattern of temperature fluctuations in the cosmic microwave background show that most of the matter in the universe is in some invisible form called dark matter, which does not interact with light in the way atoms do. Ordinary baryonic matter is a minority component by mass, yet it is the component that forms stars, planets, and the structures on which life depends. For our discussion of extreme matter, we focus on what happens when gravity acts on this familiar material and compresses it far beyond the densities typical of planetary interiors or stellar envelopes. Inside a main sequence star, matter spends most of its life as a hot plasma of ions and electrons. Nuclear fusion in the core converts light elements into heavier ones and releases energy. This energy keeps the plasma hot, and the resulting thermal pressure, along with radiation pressure in some cases, balances gravity. As long as fusion continues, the star is in a state called hydrostatic equilibrium. Gravity pulls inward, pressure pushes outward, and the overall structure changes only slowly. Even though the conditions in a stellar core are extreme by human standards, this is still normal matter in the astrophysical sense. Particles are moving fast, collisions are frequent, but the material behaves like a highly ionized gas whose properties can be captured by an almost classical equation of state. The transition toward extreme matter begins when this balance can no longer be maintained. Once nuclear fuel in a stellar core is exhausted, ordinary thermal and radiation pressure are no longer sufficient to counteract gravity. The plasma starts to contract and densities rise. At first, the matter is still basically an ionized gas, just hotter and denser. But as the collapse proceeds, electrons are forced into a smaller and smaller volume, and quantum statistics cease to be a minor correction. The Pauli exclusion principle, which quietly helped give solids their rigidity, now becomes a primary source of pressure as electrons are crowded into higher energy states, simply because lower ones are already filled. From one point of view, then, extreme matter is not made of different particles than ordinary matter. It still contains electrons, protons, and neutrons. What changes is how tightly they are packed and which physical effects dominate their behavior. Under normal conditions, electromagnetic forces and thermal motion shape the structure of matter. Under extreme conditions, gravity and quantum degeneracy take over. Understanding what counts as normal matter, with atoms, molecules, and classical plasmas, gives us the reference frame needed to appreciate just how dramatic this transition is when we follow the life of a star beyond its stable phase. For you as a listener, it can be strangely comforting to realize that the same laws that govern collapsing stellar cores also quietly support the room around you. The chair beneath you, the floor under your feet, and even the air in your lungs obey the gentle side of quantum rules that, under far stronger gravity, will create white dwarfs and neutron stars. Tonight, though, those atoms remain in their familiar, low-density arrangements, spaced comfortably apart, unhurried by any crushing force. You do not need to hold all the details of the physics in your mind. You can simply let the thought settle that the matter around you is stable, that the forces within your own body are in balance, and that for now the universe allows you to rest, carried safely by ordinary matter in its calm and familiar state. Chapter 2. When stars run out of fuel, the road to degeneracy. A star is held together by one continuous negotiation between gravity pulling inward and pressure pushing outward. For most of its long life, this negotiation feels almost effortless. The star shines steadily, its heat rising from deep within its core, where nuclear fusion converts light nuclei into heavier ones. Fusion provides the thermal pressure that prevents gravity from collapsing the star, and gravity provides the density required for fusion to continue. As long as these forces remain in balance, the star stays in hydrostatic equilibrium, changing only slowly as the ages pass. This quiet balance endures only as long as the star has nuclear fuel. In stars like our Sun, this fuel is primarily hydrogen, the simplest and most abundant element in the universe. When hydrogen nuclei collide under enormous temperatures and pressures, they fuse into helium and release energy in the process. That energy keeps the core hot, and the heat creates pressure that pushes back against gravity's inward pull. When hydrogen is plentiful, fusion replenishes the energy lost through radiation at the surface. The core remains stable, and the star maintains its familiar structure. But no fuel supply lasts forever. Although stars contain tremendous amounts of hydrogen, fusion gradually consumes it, turning it into helium. The core composition evolves, becoming richer in helium as the star ages. Eventually, the hydrogen concentration in the central region drops so low that the fusion reactions weaken. Because fusion depends very sensitively on the density and temperature in the core, the drop in fuel quickly affects the pressure output. The star's core becomes less able to push back against gravity, and gravity, patient and persistent, begins to reclaim the ground it once ceded. As the star starts to contract, gravitational potential energy converts into heat, raising the core temperature. This heating can temporarily halt the collapse, but it does not restore the original balance. Instead, the rising temperature ignites hydrogen fusion in a shell surrounding the inert helium core. For a while, this shell-burning phase supports the outer layers of the star, causing them to expand dramatically. A star like the Sun grows into a red giant during this stage. The outer helix of gases becomes enormous and cool, but deep inside the helium core continues to contract under its own weight. What happens next depends on the mass of the star. Many stars, including the Sun, do not become hot enough in their cores to ignite helium fusion until the core contracts significantly. When the temperature finally becomes high enough for helium to fuse into carbon and oxygen, the star experiences a sudden ignition of helium fusion, called a helium flash. After this event, the star regains a temporary equilibrium as helium burns in the core and hydrogen continues burning in a surrounding shell. Even this renewed balance, however, is transient. Helium fuel, too, becomes depleted. Once the helium in the core is exhausted, the fusion reactions cease again, and the core once more begins to contract. For stars not massive enough to ignite carbon fusion, this contraction is the beginning of a transformative process that will profoundly alter the nature of the matter inside. As the core shrinks, its density increases far beyond anything we encounter on Earth. Under normal conditions, atoms remain separate, each with its own electron cloud. But as the gravitational force squeezes the core, atoms are pushed closer together than their quantum structure will comfortably allow. The electrons, restricted by the Pauli exclusion principle, cannot all occupy the same low-energy states. As they are forced into fewer available positions, they begin to build up what is known as electron-degeneracy pressure. This type of pressure is not generated by heat. It exists because electrons, as fermions, must each occupy a unique quantum state. When the core becomes dense enough, the electrons create a powerful resistance to further compression, simply because all the lower energy states are filled and the remaining electrons must occupy higher momentum states. This degeneracy pressure can counteract gravitational collapse even when the core is not producing any fusion energy, giving the remnant its structural support. The development of degeneracy pressure marks the moment when matter transitions away from its familiar form. No longer a hot plasma obeying largely classical rules, the core now behaves like a quantum gas. The temperature is high, but heat no longer determines the pressure. Even if the core cools, degeneracy pressure remains. This is the principle behind white dwarfs, where the collapsed electron-degenerate core supports the star against further collapse. Before the star reaches this final state, however, its outer layers must be expelled. As fusion shuts down in the core and shell burning continues for a limited time, the outer envelope becomes unstable. Pulsations and strong stellar winds cause the star to shed its outer layers into space, forming a glowing planetary nebula. What remains behind is the compact, electron-supported white dwarf. For more massive stars, the road to degeneracy takes a different path. These stars achieve much higher core temperatures during their lifetimes and can fuse heavier elements beyond carbon. A massive star cycles through stages where its core fuses progressively heavier nuclei, carbon into neon, neon into oxygen, oxygen into silicon, and silicon eventually into iron group elements. Each successive stage requires higher temperatures and densities, and each stage burns for a much shorter time than the one before. The core structure becomes layered, resembling an onion, with shells of fusion surrounding the innermost region. Iron is a turning point on this journey. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes energy. When fusion in an iron-rich core ends, there is no further way to generate the pressure needed to oppose gravity. The core collapse accelerates catastrophically, and the electrons and protons are forced into such close proximity that they combine to form neutrons and neutrinos. This process, called electron capture, removes the electron-degeneracy pressure that had been resisting collapse, and the core falls inward with unstoppable momentum. For such massive stars, the path leads not to an electron-degenerate white dwarf, but to a neutron-degenerate object. In the aftermath of the collapse, the infalling material rebounds and creates a supernova explosion, leaving behind a neutron star supported by neutron degeneracy pressure rather than electron degeneracy pressure. But the physics of neutron stars belongs to later chapters. For now, the important point is that the collapse into degeneracy is inevitable once fusion stops providing pressure. The transition from thermally supported plasma to degenerate matter is one of the most striking transformations in astrophysics. No cooling, no ordinary pressure, and no chemical force can stop gravity once fusion ends. Only quantum mechanics can. The exclusion principle, which normally keeps matter from collapsing into itself, becomes the sole guardian that holds gravity at bay. The star reaches a new equilibrium defined not by heat, but by the quantum arrangement of electrons or neutrons. This road toward degeneracy is more than a technical detail of stellar evolution. It is the threshold where matter changes its identity. The atoms that once defined the star cease to exist as independent structures. Electrons no longer orbit nuclei. The matter becomes a dense sea of subatomic particles crowded into the lowest states nature allows. In this form, it is no longer recognizable as the matter that filled the star during its long, luminous life. Reflecting on this transformation can inspire a quiet, existential awareness. Stars live for immense spans of time, but even they cannot resist the eventual exhaustion of their internal fire. When the fuel runs out, gravity takes over, guiding the star into forms that are colder, denser, and stranger than anything we encounter on Earth. And yet, this process follows rules that are deeply ordered. There is no chaos in the collapse, only the steady unfolding of physical laws that have shaped the universe since its beginning. As you think about this, you might sense a calm recognition of your own small place in a vast cosmos where even stars must eventually change form. Their long lives end not in disorder, but in a natural settling into the states allowed by the universe. And perhaps, As you let your body rest, you can allow yourself a similar gentle acceptance that change is simply part of the story. A soft turning of the page in a universe that continues on in quiet, boundless order. Chapter 3. White Dwarfs, the realm of electron-degenerate matter. A white dwarf is one of the quietest yet most remarkable objects in the universe. It is the final evolutionary state for the vast majority of stars, including one similar to the Sun. To understand what makes a white dwarf so unusual, one must look closely at what happens when a star has burned through its nuclear fuel and can no longer support itself through the familiar mechanisms of fusion and thermal pressure. In this state, matter rearranges itself into a form that does not exist anywhere on Earth. This new form of matter is governed not by heat or chemical bonds, but by the fundamental quantum rules that restrict how electrons may occupy energy states. The result is electron-degenerate matter, a substance so dense and rigid that it resists gravity itself through nothing more than the quantum nature of electrons. White dwarfs originate in stars that began their lives with moderate masses. After spending vast stretches of time on the main sequence fusing hydrogen into helium in their cores, such stars eventually exhaust the hydrogen in their central regions. Their cores, now filled predominantly with helium, contract under gravity while hydrogen fusion continues in a surrounding shell. The outer layers expand and cool, and the star becomes a red giant. Deep within this swollen envelope, the core grows hotter and denser until it can ignite helium fusion, producing carbon and oxygen. But even helium eventually runs out. When the helium fuel becomes depleted, the core once again contracts. For stars not massive enough to ignite carbon fusion, the contraction represents the end of active nuclear burning. At this point, gravity pushes inward with a relentless force, and yet the core does not collapse indefinitely. Instead, the electrons within the carbon and oxygen nuclei become so tightly confined that quantum mechanics intervenes. The Pauli exclusion principle prohibits identical electrons from occupying the same quantum states. As gravity squeezes the core, the available low-energy states fill quickly, forcing electrons into higher energies and creating a pressure that does not depend on temperature. This electron degeneracy pressure is what allows the stellar remnant to stabilize as a white dwarf. When the outer layers of the star are ejected into space, often forming a glowing shell of ionized gas known as a planetary nebula, the core is exposed as a brilliant, compact object, roughly comparable in size to Earth, but vastly more massive. A white dwarf typically contains an amount of mass similar to that of an ordinary star, but compressed into a volume that would easily fit within a terrestrial planet. This immense density gives the white dwarf unusual physical properties. Although the matter within it consists of atomic nuclei embedded in a sea of degenerate electrons, no atom retains its usual structure. Electrons are not associated with any one nucleus. Instead, they form a collective quantum gas that permeates the entire object. Under ordinary circumstances, in a solid or liquid, atoms are arranged in regular or irregular patterns, their electrons occupying discrete orbitals around nuclei. In a white dwarf, however, the pressure is so extreme that electrons are stripped from their nuclei entirely and move as nearly free particles. The ions, mainly carbon and oxygen nuclei, settle into a closely packed lattice, often arranged in a crystalline structure. This ionic lattice is somewhat similar to a solid, but unlike the solids familiar to us, Its rigidity comes not from chemical bonds, but from the immense electrical forces between nuclei and the quantum mechanical resistance of electrons to further compression. The stability of a white dwarf depends on the delicate balance between gravity, attempting to compress the remnant further, and electron-degeneracy pressure resisting collapse. The relationship between the density of the star and the pressure provided by the electrons changes as the star becomes more compact. In low-density conditions, the electrons behave non-relativistically, and the pressure increases steadily as they are squeezed into higher momentum states. But as the density rises and electrons are forced into energies where their speeds approach the speed of light, the pressure increase becomes more gradual. This shift from non-relativistic to relativistic behavior sets a natural limit on how massive a white dwarf can be. Beyond a certain mass threshold, electron-degeneracy pressure cannot withstand gravity, and collapse becomes inevitable. This upper boundary is known as the Chandrasekhar limit, named after the astrophysicist who first calculated it using the principles of quantum mechanics and special relativity. Stars that exceed this limit at the end of their lives cannot stabilize as white dwarfs. Instead, their cores collapse further, eventually forming neutron stars or black holes. Those below the limit remain as white dwarfs for extraordinarily long periods, slowly cooling as they radiate away their residual heat. A young white dwarf is extremely hot, glowing white or blue as it emits the leftover thermal energy acquired during its formation. However, without nuclear fusion or other energy sources, it gradually cools. Over billions of years, it dims from white to yellow, then to red, and finally to a theoretical dark remnant known as a black dwarf. No black dwarfs yet exist in the universe because the universe itself has not existed long enough for a white dwarf to cool to such an extent. The timescale for such cooling is longer than the age of the cosmos, suggesting that white dwarfs are among the most enduring objects to emerge from stellar evolution. Inside the white dwarf, the structure is surprisingly uniform compared with a typical star. There is no ongoing fusion in its core, no convective cells, and no layered composition from differing fusion cycles. Instead, the interior is a near homogeneous mixture of nuclei and electrons. As the star ages and cools, the ions gradually settle into an even more structured crystalline state. There is evidence that some white dwarfs undergo crystallization in their interiors, turning vast spheres of carbon and oxygen into cosmic diamonds. Observations reveal signatures consistent with this phase transition, which releases latent heat and can momentarily delay the cooling of the star. Even though white dwarfs are stable for enormous spans of time, their physics remains extreme by any human measure. The gravity at their surfaces is so strong that a small drop in altitude corresponds to a significant change in gravitational potential. This force ensures that any material accreted from companion stars or the interstellar medium falls onto the surface with immense energy. In some binary systems, a white dwarf can draw material from a companion, gradually accumulating mass. If enough material builds up and conditions become sufficiently hot, runaway nuclear reactions can occur on the surface, producing a nova. In more extreme cases, if the white dwarf approaches the Chandrasekhar mass, the entire star can undergo a catastrophic thermonuclear explosion known as a Type 1 supernova. This detonation is powerful enough to completely disrupt the star, leaving no remnant behind and enriching the surrounding space with heavy elements synthesized during the explosion. For solitary white dwarfs or those in wide binary systems, the evolution is more peaceful. They cool quietly in the cosmic darkness, their densities unchanged, their electron-degenerate matter providing steadfast support. The electrons that once orbited individual atoms now behave collectively, each occupying a quantum state in a vast, compact Fermi sea. This peculiar form of matter represents one of the cleanest and most comprehensible examples of quantum physics on astronomical scales. Although white dwarfs seem alien compared with the familiar phases of matter on Earth, their formation follows the ordinary rules of stellar structure. They are not exotic in origin. They arise from stars that were once ordinary and stable. What makes them remarkable is not that they are the remnants of dying stars, but that they reveal, in their final form, the underlying quantum nature of matter that exists even in everyday environments. On Earth, degeneracy pressure plays almost no role in the behavior of matter because densities are far too low. But in a white dwarf, those same quantum rules become the dominant force resisting gravity itself. Reflecting on this can inspire a quiet sense of perspective. A white dwarf is a reminder that even the familiar matter around you possesses a deeper, hidden structure that only becomes visible under extreme conditions. The universe contains layers of reality that do not reveal themselves in daily life, but are always present, waiting in the background. Just as stars shed their outer layers and settle into their final compact states, we too are shaped by forces we cannot always see, guided by principles that operate quietly beneath the surface of experience. In this recognition, there is a gentle reassurance that transformation is a natural endpoint, that even after great change there can be stability, and that the universe allows all things to find a state of balance, even if it looks nothing like what came before. Chapter 4. Neutron stars, the crushing of atoms into nuclear matter. When a massive star reaches the end of its nuclear life, and fusion can no longer sustain the outward pressure to resist gravity's relentless inward pull, the star's core collapses in a dramatic and profound transformation. In that collapse lies the birth of a neutron star, an object so dense and so extreme that its very matter is rewritten. The atoms that once existed, nuclei surrounded by electrons, are destroyed or reconfigured, and what emerges is nuclear matter in a form that terrestrial laboratories cannot recreate. In this chapter, we explore how atomic structure gives way to neutron-rich matter, how the core of a collapsed star acquires the identity of a neutron star, and what this teaches us about matter in its most extreme form. In the life of a star, much more massive than our Sun, nuclear fusion proceeds through stages: hydrogen into helium, helium into carbon and oxygen, carbon into heavier elements, and finally, in the most massive cases, the formation of an iron core. At the moment the iron core fails to produce energy by fusion, the star's balance is lost. Gravity begins to dominate completely. The core compresses inwards, electrons and protons become forced together by immense pressure and fuse into neutrons and neutrinos. This process, driven by electron capture and photodisintegration of iron nuclei, precipitates a catastrophic collapse. The rebound of infalling material and the flood of neutrinos drive a supernova explosion, leaving behind a compact remnant, the neutron star. The matter of a neutron star is fundamentally different from the degenerate electron-supported matter of a white dwarf. In the core of a neutron star, the density reaches roughly nuclear density, meaning that nuclei are so close together that the space between them vanishes and neutrons and protons merge into a continuous sea. Typical densities approach values similar to those of atomic nuclei, on the order of 1 × 10⁻14 or more grams per cubic centimeter. In such a context, the matter is no longer a collection of distinct atoms. It becomes a gigantic nucleus in its own right, held together not by electron-degeneracy pressure, but by neutron degeneracy, strong nuclear forces, and gravity combined. The structure of a neutron star emerges with a layered architecture. At the outermost surface, the matter might still consist of atomic nuclei and electrons, albeit under incredible compression and magnetic fields thousands or millions of times stronger than anything on Earth. Below the surface lies the crust, where atomic nuclei are arranged in exotic lattice structures and electrons are forced into high momentum states. As the density increases further, a region emerges where free neutrons drip out of nuclei, a neutron drip zone, leading to a sea of neutrons mingling with nuclei and electrons. Deeper yet, in the outer core, the matter is dominated by neutrons, with a few protons and electrons. At the innermost core, the composition is uncertain. It may include hyperons, meson condensates, or deconfined quark matter, though the precise equation of state remains an active area of research. The term nuclear matter thus comes to denote matter at densities where nucleons, neutrons, and protons are so tightly packed that individual nuclei cease being distinct. Supporting such a massive object of extreme density demands extraordinary forces. Neutron degeneracy pressure is one of them, analogous to the electron-degeneracy pressure of white dwarfs, but much stronger. The Pauli exclusion principle, once again, forbids identical fermions, in this case neutrons, from occupying the same quantum state. As the core collapses, neutrons are forced into higher and higher momentum states, and this degeneracy contributes significant pressure. Additionally, the strong nuclear force between nucleons at very short ranges provides a repulsive component when distances become extremely small, which further helps resist gravitational collapse. The combination of these mechanisms allows a neutron star to remain in equilibrium, albeit a precarious one, rather than collapse immediately into a black hole. The mass and radius of neutron stars reflect this balance. Typical radii are on the order of 10 kilometers, yet they contain more mass than our Sun. Given these proportions, the gravity on a neutron star's surface is enormous, many billions of times stronger than Earth's. Escape velocity approaches a substantial fraction of the speed of light. Such conditions mean that matter falling onto the surface is accelerated enormously, releasing vast amounts of energy. The matter of the star is compressed to densities that defy everyday intuition. Imagine that a teaspoonful of neutron star matter would weigh billions of tons. As for rotation and magnetic fields, neutron stars are exceptional. Conservation of angular momentum means the collapsed core spins rapidly. A star that once rotated slowly can spin hundreds of times per second as a neutron star. Strong magnetic fields, often trillions of times stronger than Earth's, give rise to phenomena such as pulsars, rotating beams of radiation that sweep across space. These exotic behaviors arise because the matter inside is in such a compact, high-energy, quantum-dominated state. Let us consider the evolution of a neutron star. After the supernova explosion, the remnant is extremely hot. Temperatures can exceed millions of Kelvin. Over time, the star cools via neutrino emission and photon radiation from its surface. The interior may develop superfluid behavior. Neutrons pair up and flow without friction, protons become superconducting, and the entire interior acts like a quantum liquid. These states further transform the nature of matter within, altering how heat is transported and how magnetic fields evolve. Observations of neutron star cooling rates support the presence of such superfluid states in the deep interior of certain neutron stars. The study of neutron stars is more than astrophysical curiosity. They provide unique laboratories for dense matter physics. The equation of state, how pressure depends on density and temperature, for nuclear matter at extreme densities remains uncertain. By observing the masses and radii of neutron stars, by detecting gravitational waves from binary neutron star mergers, and by studying glitches in pulsar rotation, scientists constrain the physics of strong interactions, symmetry energy, and nucleonic behavior under extreme pressure and density. These observations reach beyond astronomy. They touch fundamental nuclear physics, quantum mechanics, and general relativity all at once. The journey from ordinary atomic matter through the degenerate electron-supported white dwarf state to the neutron-supported neutron star represents one of the most dramatic transitions in astrophysical matter. In a neutron star, the atoms as you know them no longer exist. The electrons and protons have been transformed into a neutron-rich sea, and the nature of the matter is dictated not by chemistry, but by nuclear forces and quantum statistics. This transformation is the crushing of atoms into nuclear matter. In this context, the neutron star embodies the extreme of matter's possibilities before the final collapse into a black hole. It is a testament to how the universe treats matter under overwhelming gravity and extreme density. Still, the precise interior remains mysterious. The core may hold exotic phases of matter that we can only theorize about. Quark matter, color superconducting phases, or strange matter with strange quarks. Each possibility carries profound implications, both for how we understand matter and how we interpret the life cycles of stars. As you rest and consider the existence of a neutron star spinning silently somewhere in our cosmos, remember that the same physical laws that govern the iron in your bloodstream, the atoms in your skin, and the molecules in your breath also govern these stellar remnants. The transformation of matter from atoms to neutrons and possibly beyond is not a violation of those laws, but their deeper, hidden workings exposed. In this sense, the neutron star invites us into humility. Even something as familiar as matter can be rendered alien under extraordinary conditions. And as you drift toward sleep, consider this: the atoms that compose your body might one day bear witness in distant epochs to transformations far beyond their present form, and yet within the same unchanging cosmic rules that guide all matter, all structure, all change. Chapter 5. Quark matter, when neutrons melt into their components. In the deep heart of a collapsed star, wherein the densities exceed those encountered even within a neutron star's core, the identity of matter itself may shift profoundly. What we think of as neutrons might no longer be the relevant particles, and instead the constituents of those neutrons, the quarks, may roam freely in a new state known as quark matter. In this chapter, we explore the transition from neutron-degenerate matter into quark matter, why physicists consider this phase plausible, how it might reshape our understanding of matter's ultimate limits, and what cosmic conditions could enable or reveal it. To begin, recall that neutrons are themselves composed of quarks. Up quarks and down quarks bound together by the strong nuclear force, mediated by gluons. Under normal nuclear matter densities, quarks are confined within neutrons and protons. They cannot escape the bags formed by the strong force. But if density becomes so extreme that the spacing between nucleons is compressed beyond the radius of each individual nucleon, the boundaries between these nucleons may vanish. In such an ultra-dense environment, the quarks may deconfine, becoming the relevant degrees of freedom rather than bound nucleons. This deconfinement is the essence of quark matter. The theory of quantum chromodynamics suggests that when baryon density and chemical potential become sufficiently large, the matter phase diagram shifts from hadronic matter to quark matter. The concept is partly motivated by the search for a comprehensive equation of state of dense matter, the relationship between pressure and density in a compact object. Observations of the most massive neutron stars, combined with theoretical modeling, indicate that the interior of such stars may already show evidence of behavior consistent with deconfined quark matter cores. One set of researchers found that the inferred properties of matter in the cores of the heaviest stable neutron stars are compatible with a deconfined phase and suggest the presence of quark matter. This does not mean we have direct proof of quark matter inside stars, but the possibility is increasingly taken seriously in astrophysics. If quark matter exists, its characteristics are striking. The free quarks would form a Fermi sea of up, down, and possibly strange quarks, permeated by electrons to maintain charge neutrality and by gluon fields. Because of the extreme density, the quark gas may become superconducting in the color charge sets, quarks pairing up analogously to electrons in conventional superconductors. This so-called color superconducting phase is expected in cold, ultra-dense quark matter. Indeed, recent research connects observations of compact stars to empirical limits on color superconducting pairing. If quark matter is present in the core of a neutron star, many of its observable signatures would differ from those of purely hadronic matter. Cooling rates, spin-down behavior, glitch phenomena, and gravitational wave emission during mergers may all carry subtle fingerprints of quark matter. A central aspect of the transition from neutron matter to quark matter is the idea of a first-order phase transition, or a crossover in the high-density region. If the matter inside a compact star shifts abruptly from nucleons to quarks as density rises, there may be a discontinuity in the equation of state, perhaps accompanied by a latent energy release, rearrangement of composition, and sudden changes in radius or moment of inertia. Some models suggest metastability. A neutron star might remain in a hadronic state until a critical pressure triggers nucleation of a quark matter drop, converting the core. What might this transition look like physically? Envision a neutron star core under tremendous compressive forces. The density increases until nucleons are squeezed so tightly together that their individual identities blur. The boundaries defined by the strong force between one nucleon and another vanish. Under such pressure, the nucleons may melt, their quarks liberated into a continuum. In this quark medium, the Fermi momentum of quarks is immense. The particles move almost relativistically. Because the quark medium can support pressure in new ways, through quark degeneracy, interactions via the strong force, and possibly color superconductivity, the star may achieve a new form of equilibrium beyond neutron degeneracy. Understanding the internal structure of a star with a quark core becomes a matter of astrophysics and nuclear physics meeting in a dense regime. The presence of quark matter changes the compressibility of interior layers, the speed of sound in the medium, the cooling behavior, and the star's response to perturbations. Because the equation of state of quark matter is less well constrained, observing astrophysical objects that push these limits gives physicists a rare window into the strong interaction physics of quarks at high density. In this sense, compact stars become laboratories inaccessible on Earth. If a transition to quark matter occurs, it may produce astronomical phenomena. Some models propose that a conversion of a neutron star's core into quark matter might produce a quark nova, a sudden release of energy analogous to a supernova, but driven by phase change rather than nuclear burning. The conversion would accelerate mass motion, emit neutrinos, perhaps trigger gamma-ray bursts. While hypothetical, the concept illustrates how the physics of quark matter might imprint itself on cosmic signals. The idea of strange quark matter pushes the possibility further. Strange quarks, being heavier than up or down quarks, may appear in high-density quark matter and yield a more stable configuration. Under the so-called strange matter hypothesis, strange quark matter could be absolutely stable, meaning that an ordinary nucleon could potentially decay into strange quark matter if conditions allowed. While no evidence yet confirms strange stars, the concept illustrates the breadth of possibility once quark matter is taken seriously. One must always remember the uncertainties. The very high-density, low-temperature regime relevant to compact stars is not accessible via terrestrial experiments. Lattice quantum chromodynamics struggles at high chemical potential. Modeling relies on effective theories, approximations, and astrophysical constraints. Many possible phases of quark matter exist in theory. Color flavor locked phases, gapeless phases, crystalline loft structures, and the transitions between them remain speculative. Nevertheless, the intersection of observational data, for example from gravitational wave detectors, X-ray timing, radio pulsars, and theoretical work is narrowing the possibilities. From a structural viewpoint, a compact star with a quark core could still retain a hadronic outer mantle, creating a so-called hybrid star. Within it, pressure and composition change with radius. A crust of nuclei and electrons, a mantle of neutron-rich nuclear matter, a core of strange or deconfined quarks. The star's mass-radius relationship, moment of inertia, and tidal deformability in binary mergers may all reflect internal layering. Current observations suggest that the most massive neutron stars may indeed require a softer equation of state at high density, compatible with quark matter cores. Beyond the astrophysical, the existence of quark matter holds deep physical significance. It indicates that matter is not fixed in one immutable form, but rather evolves under pressure and density. At the highest densities, nature chooses a different set of particles, excitations, and collective behaviors. The quark phase shows that the building blocks of matter can change under extreme conditions. In a way, it reframes how we conceive of stability, structure, and identity in the universe. Instead of atoms, nuclei, neutrons, we now imagine a path toward quarks, color superconductivity, perhaps something even stranger still. The very idea invites reflection. If the densest matter in the universe reorganizes itself into quark matter, then the identity of something as seemingly familiar as a neutron star may be largely defined by particles we cannot observe directly, interacting in ways we cannot yet reproduce. In this sense, the quark matter hypothesis draws us to humility. We recognize that our everyday matter is but one expression of physical laws, and under more extreme conditions, those laws manifest entirely new states. As you rest tonight, imagine for a moment the hidden heart of a collapsed star, a region smaller than a city, denser than a mountain, where quarks roam free and matter as we know it dissolves into something new. In that quiet cosmic forge, the boundaries of atoms vanish and the universe reveals an underlying fluid of fundamental particles. Let the thought wash through your mind slowly and allow a sense of cosmic continuity to settle. The matter in your body follows the same laws that shape these distant extremes. And even in the darkest, smallest corners of the universe, change leads to new order, new states, and in that silent transformation, a deep and enduring calm. Chapter 6: Nuclear Pasta and the Exotic Architecture of Neutron Star Crusts. In the inner crust of a collapsed star, as the density grows beyond familiar atomic thresholds, but before the core transforms fully into the neutron-rich fluid of the deep interior, matter arranges itself into strange, non-intuitive geometrical patterns. This region is home to what astrophysicists call nuclear pasta, a name chosen because the shapes formed by nuclei and neutrons under immense pressure resemble the everyday pasta served at dinner: sheets, tubes, rods, and bubbles. But here the setting is anything but ordinary. The competition between the short-range nuclear attraction and the long-range Coulomb repulsion, combined with the relentless squeeze of gravity, gives rise to these exotic forms. Understanding nuclear pasta is essential for grasping the physics of the crust of a neutron star and how matter behaves when it is both dense in a nuclear sense and far from equilibrium. Consider the crust of a compact object like a neutron star. Just below the surface there are atomic nuclei of elements such as iron or nickel, arranged in a solid lattice embedded in a sea of electrons. As the pressure and density increase deeper into the star, the nuclei become increasingly neutron-rich. They accumulate extra neutrons because the equilibrium of protons, neutrons, and electrons shifts under compression. Eventually, the neutrons begin to drip out of the nuclei and form a neutron fluid permeating the lattice. This zone is the inner crust, and deeper still, one reaches a transition region where the very identity of nuclei becomes unstable. It is here that nuclear pasta appears, matter in which nuclei are deformed and fused, producing complex architectures that minimize the total energy in the face of gravity, nuclear force, and electrical repulsion. In this exotic layer, the size of a representative nucleus is no longer a few femtometers quietly surrounded by electrons. Instead, you have structures of thousands of nucleons, extended into rods or sheets, immersed in a neutron fluid. The shapes emerge because the system is frustrated. To borrow a term from condensed matter physics, meaning there is no arrangement that simultaneously satisfies every force. The strong nuclear force tends to pull nucleons together into tight clusters. The Coulomb force pushes protons apart. Gravity pulls everything inward, and the electron gas also exerts pressure. Because no simple sphere of nucleons yields the lowest energy, matter resolves into elongated rods, flattened sheets, tubes, and networks of voids and filaments. Hence gnocchi, spaghetti, lasagna, Even waffle and anti-spaghetti phases appear in the lexicon of nuclear pasta theory. One of the most striking features of nuclear pasta is its predicted rigidity. Simulations show that these structures are far stronger than any known material under terrestrial conditions. This has consequences for the crust's mechanical behavior. The maximum height of mountains on a rotating neutron star, the way the crust cracks, and how elastic energy is stored and released are all influenced by the presence of pasta layers. Because the crust can sustain larger stresses when pasta is present, the star may develop irregularities whose mass distribution can produce continuous gravitational wave emission. In effect, the crust becomes more solid than if only spherical nuclei were present. The pasta layer might form nearly half the mass of the crust in some models, and yet occupy only a fraction of its thickness, a thin but potentially dominant contributor to the star's structural and thermal behavior. The transport properties of the nuclear pasta region are equally important. The flow of heat, the conduction of electricity, the emission of neutrinos, all depend on matter's microstructure. In the pasta zone, electrons are scattered by complex geometries, and neutrons in the fluid phase interact with the nuclei and rods. Electron and neutron conduction are suppressed relative to simpler crystalline lattices. This suppression may affect how the crust cools, how magnetic fields decay, and how sudden flares in magnetars and other compact stars behave. Because neutron star crusts cool through neutrino emission and photon conduction, modifications introduced by pasta can alter the thermal evolution observable over many thousands of years. Thus, the seemingly arcane shapes of nuclear pasta have far-reaching consequences for how these exotic stars appear to us. The layering in the crust then proceeds from outer to inner. A lattice of heavy nuclei and electrons, a region of nuclei immersed in a neutron fluid, then the pasta zone where nuclei fuse into extended shapes, and finally, the uniform nuclear matter of the core. At the interface between the pasta and the core, the voids shrink away, the rods merge into sheets, the sheets collapse into uniform matter, and matter changes from being cluster plus fluid into the homogeneous nuclear liquid of the core. The exact densities and transition pressures depend on the equation of state for dense matter, as yet uncertain, and on the symmetry energy that determines how neutrons and protons behave under compression. As recent research shows, the nature of the pasta phases is strongly influenced by the slope of the nuclear symmetry energy at subsaturation densities. Observational clues suggest nuclear pasta is more than theoretical. For example, the decay rates of magnetic fields in isolated neutron stars and the maximum spin periods observed hint at the presence of a high impurity, rigid layer inside the crust. Some sudden gamma-ray flares of magnetars may be triggered by fractures in the pasta layer. Simulations of neutrino transport in core collapse supernova show that the pasta layer can trap neutrinos, affecting the cooling of the protoneutron star and the neutrino-driven wind that enriches the surrounding space. All of these threads point to the reality of nuclear pasta as a region of transition, a zone where we see familiar nuclei give way to the unexpected. From a physical perspective, nuclear pasta is a unique astromaterial. It combines aspects of solid-state physics, nuclear physics, and astrophysical compression. Molecular dynamics simulations reveal that the spaghetti and lasagna-shaped clusters freeze into a glassy, amorphous solid at sufficiently low temperatures. Domains of rods and sheets form with differing orientations, Electron scattering off these domains leads to increased electrical resistivity and altered thermal conduction. The result is a crust interior that is static on long timescales but active in terms of quantum and thermal behavior. In this domain, matter flows not as a gas or liquid, but as a highly interlocked network of nucleonic structures embedded in a superfluid neutron and superconducting proton background. This complex microarchitecture challenges our usual notions of material phases and invites reflection on how nature arranges matter under extreme conditions. The interplay of forces here is subtle yet dramatic. Gravity compresses, the strong nuclear interaction binds nucleons, the Coulomb force repels protons. Electrons create degenerate pressure and a conductive fluid. The neutron fluid exerts pressure and thermal conduction. The matter reorganizes to minimize total energy across all these effects. The resulting geometry is a compromise, but also extremely efficient. Fewer nuclear surface area contributions, less Coulomb energy, strong binding. What emerges is not chaos, but clever adaptation under pressure. The star finds a configuration that reduces free energy under constraints, and the rules of quantum mechanics, nuclear physics, and electromagnetism let it do so. As you listen quietly to the idea of these pasta shapes inside a distant star, imagine the familiar cables of power and the wires in your home becoming rods of nuclear material, thousands of times stronger than steel, arranged in patterns unseen on Earth. Consider how the crust of a neutron star, many kilometers below its visible surface, holds a structure threaded with sheets and tubes of nucleons. Precisely because the universe allows matter to form such exotic architectures under extreme conditions. The recognition that beneath your feet, the solid ground is held together by electrons and nuclei in a lattice is akin to the recognition that deep beneath a neutron star's surface, the matter arranges into this pasta regime. In the grand scheme, nuclear pasta reminds us that matter does not always behave the way we expect. Under familiar conditions, atoms dominate. Under these extreme ones, clusters of nucleons merge and reshape. It tells us that as matter is pushed ever harder, its structure evolves. Geometry changes, phases merge, and what seemed stable becomes flexible in a new form. And if you allow the thought to travel beyond the technical, you might sense that your own structure, your body, your consciousness, the atoms that compose both, is subject to the same physical laws that allow such exotic forms. In that recognition, there is solace. Change is built into the fabric of reality. Complexity grows in response to pressure, and the universe finds order even where density narrows everything to quantum geometry. Rest now, knowing you are part of a cosmos where even matter can become poetry, quietly reshaping itself in patterns far beyond everyday vision. Chapter 7: Superfluids, Superconductors, and Quantum Oceans Inside Stars. Deep within a neutron star, far below the crust where nuclear pasta twists into sheets and filaments, the matter undergoes yet another transformation. At densities and pressures unmatched anywhere else in the universe, the neutrons and protons that make up the core begin to behave not as a classical fluid, but as a vast quantum liquid. In this realm, particles pair up in a cooperative dance that allows them to move without resistance or electrical dissipation. The result is a mixture of superfluid neutrons and superconducting protons, forming what many physicists call a quantum ocean. This extraordinary state of matter, predicted by nuclear theory and supported by astrophysical observations, plays a central role in the behavior, evolution, and observational signatures of neutron stars. To understand how such quantum states arise, one must first recall what distinguishes superfluidity and superconductivity from ordinary forms of matter. In laboratory settings on Earth, superfluidity is typically observed in liquid helium at temperatures near absolute zero. Superfluid helium can climb walls, leak through microscopic pores, and flow without friction indefinitely. Superconductivity, likewise, is observed in certain metals and alloys cooled to extremely low temperatures, where electrons form pairs and conduct electricity with zero resistance. In both cases, the transition into these states is governed by quantum mechanics on macroscopic scales. Individual particles lose their separate identities, and their wave functions lock together into a coherent collective state. Inside a neutron star, the conditions that foster these exotic states are vastly more extreme. The interior temperature, although initially immense after formation, drops rapidly as the star cools by emitting neutrinos and photons. Within a short astronomical timescale, the temperature falls below thresholds predicted for nucleon pairing, causing neutrons to form Cooper-like pairs similar to electrons in superconductors, and protons to pair as well. Unlike terrestrial materials, however, the density at which these transitions occur is on the order of nuclear densities, 1 trillion times the density of water. At these densities, the quantum mechanical nature of nucleons is unavoidable, and the pairing interactions arise from nuclear forces rather than weak electromagnetic interactions. The first major component of this quantum ocean is the neutron superfluid. Neutrons dominate the composition of neutron stars, especially in the inner crust and core. When the temperature becomes sufficiently low, attractive components of the strong nuclear force allow neutrons to couple into pairs. These pairs act as composite bosons, permitting them to condense into a coherent quantum state. A neutron superfluid shares many of the counterintuitive properties of laboratory superfluids, but on a cosmic scale. It can flow with no internal viscosity, and it supports quantized vortices, whirlpools of circulation that carry angular momentum in discrete units rather than continuous values. These vortices play a fundamental role in the rotational behavior of neutron stars. The second component, the proton superconductor, forms because a small fraction of the nucleons in the core are protons. Although protons are charged and thus repel one another through electromagnetic forces, the strong nuclear interaction still allows pairing at sufficiently high density and low temperature. Paired protons behave as bosons, condensing into a superconducting state that can carry electrical currents indefinitely without resistive losses. This superconducting component interacts strongly with the magnetic field of the neutron star. Instead of allowing the magnetic field to pass freely, the superconducting proton fluid forces magnetic flux into quantized flux tubes. Each flux tube carries a fixed quantum of magnetic flux, and together they form an ordered array that threads the quantum interior. One of the most intriguing aspects of this quantum interior is the interplay between the neutron superfluid vortices and the proton superconducting flux tubes. The neutron vortices carry angular momentum, while the flux tubes carry magnetic field lines. Where these structures intersect, they interact strongly, setting up friction-like forces and pinning effects. This coupling between superfluid and superconducting components is believed to explain the sudden rotational irregularities, known as glitches, observed in pulsars. Glitches occur when the crust of the neutron star suddenly speeds up its rotation, relative to the expected gradual slowdown caused by electromagnetic radiation. One leading model suggests that neutron vortices pinned to structures in the crust or flux tubes in the core suddenly unpin and transfer angular momentum to the crust, producing an abrupt spin-up. The quantum interior of a neutron star, therefore, has macroscopic observational consequences detectable across thousands of light years. Another key property of superfluid and superconducting cores is their strong influence on neutron star cooling. A newly formed neutron star cools rapidly by emitting neutrinos, ghost-like particles that escape the star easily. The presence of superfluids alters how neutrinos are produced and how they interact with matter. Neutron and proton pairings suppress some neutrino-producing reactions, but enhance others, especially through a process known as Cooper pair breaking and formation. Observations of thermal emission from young neutron stars, such as the one in the Cassiopeia A supernova remnant, suggest rapid cooling consistent with the onset of neutron superfluidity. These observations represent some of the strongest evidence for superfluid matter in the cosmos. The mechanical behavior of neutron stars is also shaped by the presence of these quantum phases. In a purely classical fluid star, rotation would be smooth, and the distribution of material would adjust continuously with external forces. In a star with a superfluid interior, however, rotation is quantized through vortices. Large-scale motions, crust-core coupling, and even seismic vibrations behave differently when much of the mass is in a superfluid state. This distinction affects how the star responds to tidal interactions in binary systems, how it radiates gravitational waves, and how it behaves immediately following the merger of two neutron stars. Indeed, recent detections of gravitational waves from neutron star mergers provide new opportunities to probe the superfluid and superconducting nature of stellar interiors by comparing observed waveforms with predictions that incorporate quantum hydrodynamics. The extreme magnetic fields seen in magnetars, a class of neutron stars with particularly strong fields, are also influenced by superconductivity. In a superconducting core, magnetic fields can only enter in the form of quantized flux tubes. If the magnetic field is exceptionally strong, the superconducting state may be partially suppressed or rearranged. How magnetic energy is stored and released, how cracks or shifts in the crust behave, and how magnetars produce their intense flares are all tied to the microscopic configuration of flux tubes in the superconducting interior. This is an example of how microscopic quantum behavior governs macroscopic astrophysical phenomena. All of these factors, rotational glitches, cooling curves, magnetic field evolution, gravitational wave signatures, point to a neutron star interior that is not a simple nuclear fluid but a structured quantum fluid. And yet, despite the remarkable insight gained from observations, many uncertainties remain. The exact density dependence of nucleon pairing, the transition between crustal and core superfluid behavior, the possibility of multiple superfluid phases, and the role of exotic particles like hyperons or deconfined quarks are all active areas of research. The extreme densities of neutron stars prevent laboratory experiments from reproducing these conditions. Only indirect evidence from astrophysical measurements can illuminate the nature of these quantum motions. Nevertheless, the basic picture remains robust. Neutron stars contain matter in states that reveal quantum mechanics, not in the microscopic realm of atoms, but in large-scale astrophysical bodies the size of cities. In these environments, the laws of physics conspire to produce frictionless liquids and perfect conductors under pressures billions of times greater than anything on Earth. Matter becomes fluid in a way that defies ordinary intuition, with vortices, flux tubes, and coherent quantum states shaping the life of the star. Stepping back, the existence of these quantum oceans serves as a profound reminder of the unity of physics. The same principles that allow a laboratory sample of helium to become a superfluid or a piece of metal to become superconducting also govern the behavior of matter crushed in the heart of a neutron star. The scale may differ by astronomical factors, but the underlying rules do not. Quantum mechanics, with all its counterintuitive elegance, extends its reach from the smallest particles to the densest stellar remnants. And perhaps as you let this thought settle, there is something quietly comforting in it. The universe is full of extremes you will never touch, yet the laws that shape those distant objects are the same laws that shape you. Even in the most compressed, silent, frigid heart of a neutron star, the structure of matter follows a kind of cosmic order. In that realization, you may find a moment of stillness, a sense that even amid unimaginable forces and densities, the universe remains coherent and continuous, and you, in your own small corner of it, are part of the same long, unbroken story. Chapter 8. Exotic matter around black holes, accretion disks, and tidal compression. Around a black hole, matter enters one of the most extreme environments in the universe. Unlike the interior of a neutron star, where the density of matter itself becomes extraordinary, the physics near a black hole arises not from the internal structure of matter, but from the gravitational field imposed on it. Whether the black hole formed from a collapsed star or the steady consumption of interstellar gas, its gravitational influence creates conditions where matter is heated, stretched, torn apart, and accelerated to relativistic speeds. The result is a domain where ordinary plasma becomes extraordinary, radiation becomes a dominant pressure source, and matter behaves in ways that no terrestrial laboratory could reproduce. The first major structure to form near a black hole is the accretion disk. When gas, dust, or stellar debris falls toward a black hole, it rarely plunges straight in. Instead, it carries angular momentum, causing it to orbit the black hole at high speed. Because the gravitational pull is strongest near the center, the inner regions of the disk orbit faster than the outer regions. This differential rotation creates friction and shear, which heat the material. As the disk becomes hotter, its particles reach temperatures of millions of degrees, often hotter than the cores of main sequence stars. At such high temperatures, matter cannot exist in solid or liquid form. It becomes a fully ionized plasma consisting of atomic nuclei separated from their electrons. Because the gas is so hot and so rapidly orbiting, the accretion disk becomes luminous. Around stellar mass black holes, it emits strongly in X-rays, while around supermassive black holes, the emission spans from infrared to ultraviolet and sometimes into X-rays. Although the black hole itself emits no light, the disk around it can outshine entire galaxies. This intense luminosity is the signature of one of the most efficient energy release mechanisms known in astrophysics. The gravitational potential energy of infalling matter is converted into heat and radiation with an efficiency far exceeding nuclear fusion. The plasma within an accretion disk is threaded by strong magnetic fields. These fields originate from the motion of charged particles and from any magnetic flux brought in by infalling material. In the turbulent, differentially rotating disk, these fields are stretched, twisted, and amplified. One of the most important mechanisms that arises in this environment is the magnetorotational instability, which transports angular momentum outward, allowing matter to move inward toward the event horizon. Without this magnetic turbulence, the disk would not efficiently accrete. The fields also create jets, narrow beams of relativistic plasma expelled along the black hole's rotation axis. Although jets are not exclusive to black holes, those produced near supermassive black holes can extend for thousands of light years. Closer to the black hole, within a few gravitational radii of the event horizon, matter enters a region where the curvature of spacetime becomes dominant. In this inner zone, tidal forces grow extremely large. Tidal force refers to the difference in gravitational pull between 2 points. When the gradient becomes extreme, objects are stretched along the direction of gravity and compressed in the perpendicular directions. Around smaller stellar mass black holes, these tidal gradients become strong enough to disrupt stars entirely. A star passing too close may be torn apart in an event known as a tidal disruption. The stellar debris, once bound together by self-gravity, is stretched into long streams. Some of the material is accreted onto the black hole, producing a temporary flare that can outshine the entire host galaxy. Within the accretion flow itself, these tidal effects compress and heat matter to even higher energies. As particles spiral inward, their orbits become unstable. The innermost stable circular orbit marks the point beyond which stable orbital motion cannot exist. Inside this radius, matter plunges inward almost freely. In these final orbits, matter is moving at significant fractions of the speed of light. Under such conditions, the behavior of the plasma is governed by general relativity. Orbital frequencies, energies, luminosities, and even the perceived temperature of the disk depend on the curvature of spacetime. The exotic nature of matter in the accretion disk includes several key features. First, the plasma becomes optically thick in some regions, meaning photons are trapped and must undergo many scatterings before escaping. In other regions, the plasma becomes optically thin, meaning photons escape quickly, carrying energy away. The competition between radiative cooling and heating determines the disk structure. Second, radiation itself becomes a pressure source. When photons exert pressure on charged particles, this radiation pressure can support the disk against collapse or contribute to instabilities. Third, particle interactions become relativistic. Electrons and protons collide at energies high enough to produce gamma-ray photons, electron-positron pairs, and non-thermal radiation observed in X-ray and gamma-ray bands. Yet the accretion disk is not the only place where exotic matter appears. Infalling matter crossing the event horizon experiences gravitational time dilation. From the perspective of an external observer, the matter seems to slow and fade as it approaches the horizon, never quite disappearing, but instead becoming redshifted until it vanishes from view. From the perspective of the matter itself, however, it crosses the horizon in finite proper time. Although the internal fate of matter inside the horizon lies beyond direct observation, general relativity predicts that tidal compression intensifies dramatically as matter moves inward. Eventually, the tidal forces become so strong that they overwhelm all known internal forces, spaghettifying the particles and stretching them along the direction of infall while crushing them laterally. While the physics inside the horizon is uncertain, The region just outside the horizon is a playground for extreme astrophysics. Hot spots, plasma clumps, and magnetic reconnection events occur as turbulent magnetic fields realign. Observations by radio interferometric arrays capable of imaging the shadow of a black hole have begun to reveal these regions directly. The Event Horizon Telescope image of a supermassive black hole's accretion flow shows the asymmetric brightness caused by relativistic beaming, as matter moving toward us appears brighter than matter moving away. This observation confirms many predictions of general relativity and helps constrain the physics of the plasma swirling near the horizon. The role of accretion extends beyond individual black holes. It affects galaxy evolution and large-scale structure. Supermassive black holes at galactic centers regulate star formation through feedback. Outflows and jets driven by accretion heating expel gas from galaxies, suppress cooling, and shape the evolution of galaxy clusters. The exotic behavior of matter near black holes therefore influences cosmic history on scales far beyond the event horizon. Although the physics of accretion disks may appear unrelated to the ultra-dense matter of neutron stars or the quark matter hypothesized in extreme cores, the common thread is that matter under extreme gravity reveals aspects of physics that remain hidden in ordinary environments. In neutron stars, matter is squeezed until quantum forces dominate. Near black holes, matter is shredded, heated, and accelerated by space-time curvature. Both extremes demonstrate that the identity of matter is never fixed. It changes depending on the forces acting upon it and the environment in which it finds itself. Stepping back, there is something quietly reflective in imagining matter orbiting a black hole. It begins as cold gas drifting between stars, or as the body of a disrupted star, or as debris from interstellar clouds. Drawn inward by gravity, it loses identity, heats, glows, stretches, and ultimately vanishes into the dark interior from which no light can return. Yet in doing so, it becomes part of a cosmic process that has shaped galaxies, ignited quasars, and illuminated the universe across billions of years. As you let this thought settle, imagine that even in the most violent regions of the cosmos, there is an underlying order. Matter does not fall into chaos. It follows laws that guide it even as it spirals into darkness. And perhaps, in that recognition, there is a quiet reminder for your own experience, that even when things seem to stretch, strain, or fall apart, they may still be part of a larger, coherent flow, one that moves steadily forward, guided by forces deeper and steadier than any moment of turbulence. Chapter 9. The Physics of Collapse. Why matter cannot resist gravity forever. In the grand architecture of the universe, gravity is the quiet engineer that shapes stars, planets, and galaxies. It is the force that gathers diffuse gas into shining suns, the force that sculpts the spiral arms of galaxies, and the force that eventually drives a star toward its end. But gravity is also relentless. Once nuclear fuel dwindles and thermal pressure weakens, gravity does something profound. It presses matter into deeper and deeper forms, revealing layers of physics inaccessible under normal conditions. In this chapter, we explore the fundamental reason why matter cannot resist collapse indefinitely, even when quantum forces intervene. The journey from ordinary matter to degenerate matter and eventually to black holes is not a failure of structure, but an inevitable consequence of how gravity interacts with the building blocks of nature. To understand why collapse is inevitable under certain circumstances, it is useful to begin with the equilibrium that keeps a star stable for most of its life. In a healthy star, gravity pulls inward, while thermal pressure, generated by nuclear fusion, pushes outward. This balance is called hydrostatic equilibrium. As long as fusion continues at the appropriate rate, the star neither collapses nor expands uncontrollably. The lighter elements fuse into heavier ones, releasing energy that maintains internal pressure. But the sequence of possible fusion reactions is finite. Once a star has exhausted the fuels that are energetically favorable to fuse, the pressure drops and gravity begins to dominate. The collapse that follows is not a smooth and gentle contraction. It is a cascade of increasingly intense transformations in matter. At first, as the star cools and contracts, electrons become the dominant source of pressure. Their inability to occupy the same quantum state gives rise to electron-degeneracy pressure. This form of pressure is independent of temperature. Even a cold electron gas can resist compression due to the Pauli exclusion principle. In white dwarfs, this quantum pressure supports the entire star, preventing further collapse as long as the mass remains below a critical threshold. However, electron degeneracy pressure has limits. When the density becomes too high and the mass too great, electrons are forced into energy states where they approach relativistic speeds. As the electrons become ultra-relativistic, the relationship between pressure and density shifts in a way that weakens the pressure's ability to counter gravity. Eventually, a mass is reached beyond which electron degeneracy cannot provide adequate support. The white dwarf collapses further. If the mass is just slightly above this limit, the electrons combine with protons, producing neutrons and neutrinos, and the star becomes a neutron star. Within a neutron star, an even stronger form of degeneracy pressure appears: neutron degeneracy. Neutrons, being fermions, also obey the exclusion principle. A sea of neutrons, densely packed and forced into increasingly higher momentum states, produces an enormous pressure. Combined with the short-range repulsive component of the strong nuclear interaction, this pressure can support the neutron star against gravity, but only up to another limit. If the star is too massive, neutron degeneracy and nuclear repulsion are insufficient. No known force can sustain the overwhelming pull of gravity, and the star collapses again. At this stage, matter can no longer maintain any recognizable form. Protons and neutrons may fragment into quarks, and even quark matter, if it exists, cannot provide unlimited resistance. As the collapse proceeds, general relativity becomes essential in describing what happens. Gravity is no longer adequately understood as a force acting on matter. Instead, it becomes curvature of space-time itself. The collapse warps space-time ever more strongly, and as the density and pressure increase, the gravitational field intensifies. The key realization from general relativity is that when enough mass is confined to a sufficiently small radius, no physical force can prevent further collapse. The concept of escape velocity becomes crucial. In Newtonian gravity, escape velocity increases as the mass and compactness of an object increase. When the escape velocity reaches the speed of light, a boundary forms beyond which nothing, not even light, can escape. This boundary is the event horizon of a black hole. At this threshold, collapse becomes irreversible. According to classical general relativity, once an event horizon forms, the matter within it continues to collapse toward a singularity, a region of infinite curvature where the known laws of physics break down. While singularities remain theoretical, the formation of an event horizon is a robust prediction confirmed by observations of gravitational waves, accretion disks, and strong gravitational lensing around massive compact objects. The collapse to a black hole is not speculative, it is an observable astrophysical phenomenon. And at the heart of this process lies the fundamental principle that no known form of matter can resist gravitational collapse once certain density and mass thresholds are exceeded. To appreciate the inevitability of collapse, one must consider the competing roles of quantum mechanics and gravity. Quantum mechanics gives matter structure. Atoms resist compression through electron clouds. Degenerate fermionic gases generate pressure by filling quantum states. Nuclear forces provide repulsion at short distances. These mechanisms work effectively over an enormous range of densities, enabling planets to hold their shape, white dwarfs to persist, and neutron stars to survive extreme compression. But gravity scales with mass, and quantum forces do not. As the mass increases, the gravitational field strengthens, deepening the curvature of space-time. Meanwhile, quantum pressures increase sublinearly or reach plateaus. This mismatch means that no matter how exotic or compressed matter becomes, gravity can eventually overcome it if enough mass is present. The collapse itself is also influenced by relativity in another way. Pressure contributes to gravity. In general relativity, not only mass but also energy and pressure generate gravitational fields. In the cores of neutron stars, the pressure is so immense that it contributes significantly to the star's gravitational pull. This feedback loop, pressure increasing gravity and gravity increasing pressure, accelerates collapse. When matter becomes ultra-relativistic, the pressure behaves in a way that amplifies gravitational effects rather than counteracts them. As matter approaches collapse into a black hole, tidal forces also intensify drastically. These tidal forces stretch matter along the direction of the gravitational gradient and compress it laterally. For stellar mass black holes, tidal forces near the event horizon can be destructive. Anything falling in is shredded by these gradients long before reaching the horizon. For supermassive black holes, the tidal forces at the horizon are milder, and an object may cross the horizon intact before being torn apart. In both cases, however, once inside the horizon, no classical force can halt the collapse. The entire process stands as a dramatic demonstration that matter's stability is conditional. It depends on the balance between pressure and gravity. When nuclear pressure and degeneracy pressure are strong enough, matter can resist collapse. But those pressures have ceilings, and gravity does not. There always exists a scale at which gravitational energy dominates all competing forces, driving matter beyond any equilibrium configuration. This is why matter cannot resist gravity forever. The physics of quantum mechanics and the strong nuclear interaction cannot generate infinite pressure. Once mass and density surpass certain limits, collapse continues until an event horizon forms. Beyond that horizon lies a region sealed off from the rest of the universe, where space-time itself flows inward. Reflecting on this process reveals a quiet truth about the universe. Everything that forms eventually transforms. Stars that burn brightly for billions of years collapse when their inner engines fade. Matter that once supported fusion and generated light becomes compressed into new forms, losing its familiar identity along the way. What appears catastrophic from one perspective is simply a natural extension of physical laws at higher scales. And perhaps as you let this thought settle, you may sense a calm understanding that even in collapse, there is order. Gravity does not destroy purposefully. It simply follows its nature, shaping matter according to deep principles that have held true since the universe began. Just as stars rise, shine, and eventually fall inward, so too do experiences, moments, and challenges complete their cycles. And in that recognition that endings are transitions shaped by fundamental forces, there is a certain quiet reassurance, a reminder that change, even when profound, is part of the same steady rhythm that guides the cosmos. Chapter 10. Are there states of matter we haven't met yet? In the vast expanse of the universe, matter is constantly pushed into environments that stretch the known boundaries of physics. On Earth, matter exists in familiar phases such as solids, liquids, gases, and plasmas. In laboratories, physicists have created more exotic states like Bose-Einstein condensates, superfluids, and superconductors. In earlier chapters, we explored the extraordinary phases found in stellar remnants: Electron-Degenerate matter in white dwarfs, Neutron-Degenerate matter in neutron stars, nuclear pasta in the crust, and even the possibility of quark matter deeper within. These represent some of the most extreme manifestations of matter we have theoretical or observational reasons to believe exist. But are they the end of the story? Or does the universe contain phases of matter we have not yet discovered, states that emerge only under conditions too extreme for our current theories to describe? In this closing chapter, we explore the open frontier, the possible states of matter that lie beyond today's understanding, hinted at by theoretical physics and astrophysical mysteries. The possibility of unknown forms of matter begins with the fact that the standard model of particle physics, although extraordinarily successful, is incomplete. It describes familiar particles and interactions: quarks, leptons, photons, gluons, the weak force carriers, and the Higgs field. But it does not explain dark matter, dark energy, the unification of forces, or quantum gravity. If the basic blueprint of the universe contains components we do not yet understand, then the phases of matter built from these components must also remain unknown to us. Even within the standard model, the behavior of matter at ultra-high density, temperature, or chemical potential is poorly constrained. This leaves open an enormous landscape of possible states. One compelling direction arises from dark matter. Although its nature remains unidentified, dark matter is known to make up most of the matter content of the universe and to interact gravitationally with normal matter. Depending on what dark matter is, whether massive weakly interacting particles, axions, sterile neutrinos, or something even more exotic, it may form its own phases. Unlike baryonic matter, dark matter might not cool, condense, or fragment into atoms and molecules. But under certain conditions, it could form clumps, superfluid states, or macroscopic objects, such as dark stars or dark halos that behave like unseen matter structures. Some theories propose that dark matter could have self-interactions, leading to fluid-like or condensed phases, distinct from anything exhibited by ordinary particles. Axions, if they exist, offer a particularly intriguing possibility. Axions are hypothetical particles that could form a Bose-Einstein condensate on cosmic scales. If such a condensate forms, it could behave like a superfluid, giving rise to phenomena like vortices, waves, and collective modes. In this scenario, galaxies might rotate the way they do, not because dark matter is particle-like in the usual sense, but because it behaves as a cosmos-sized quantum fluid. This represents an entirely new state of matter, one that spans not tiny laboratory samples, but entire galaxies. Another theoretical frontier lies in states of matter beyond quark deconfinement, at densities far exceeding those believed to exist even in neutron star cores. Quarks might not simply form a Fermi sea. They could enter color superconducting phases, crystalline quark phases, or more symmetric condensates. The color flavor locked phase, for example, is a state theorized to occur at extremely high densities and low temperatures, where up, down, and strange quarks pair in symmetric patterns. If such a phase exists, it would represent a form of matter more symmetric and tightly bound than nuclear matter. Although purely theoretical at present, these phases emerge naturally from the mathematics of quantum chromodynamics once certain densities are exceeded. Even more speculative possibilities include states composed of entirely new particles predicted by extensions of the Standard Model. Supersymmetry, if realized in nature, introduces a host of additional particles, superpartners of known fermions and bosons, each of which could potentially form new bound states, condensates, or collective behaviors. In such a framework, matter might exist in phases composed of neutralinos, sneutrinos, or gluinos. While experimental searches have not yet revealed these particles, they remain possible in some versions of theoretical physics. If they exist, their collective phases could have shaped the early universe, or might still exist in regions of extreme density. Beyond the particle content of matter, space-time itself may host exotic states. In extremely energetic or dense conditions where quantum gravity becomes relevant, the fabric of space-time might not behave classically. Some theories propose the existence of space-time foam, where the geometry fluctuates at incredibly small scales. Others suggest that near singularities, or at the beginning of the universe, matter and space-time might merge into a pre-geometric phase lacking familiar spatial or temporal structure. If such states existed during the early universe, the remnants of their transitions could influence cosmic background radiation or gravitational wave signals, cosmic strings, domain walls, and other topological defects. Remnants of symmetry breaking in the early universe provide another form of exotic matter. These structures are not matter in the usual sense, but regions where fields take on different values. They could be incredibly dense, stable, and narrow, extending over astronomical distances with immense tension. If they exist today, they would represent a fundamentally new type of matter-structure hybrid, one whose physics arises from topological rather than particulate origins. Even within astrophysics, there are states that remain hypothetical due to observational limits. Strange stars, composed almost entirely of strange quark matter, would be smaller and more compact than neutron stars. Boson stars, composed of hypothetical scalar particles like axions, would be held together not by pressure, but by self-interaction of the field that composes them. These stars, if real, would not have a crust or nuclear layers. Instead, they would behave as giant, self-sustaining waves of quantum matter. Some models even propose electroweak stars, or preon stars, where matter is compressed beyond quark levels into deeper constituents, if such constituents exist. While speculative, these models are grounded in attempts to explore the limits of matter under extreme gravity and to test the consequences of beyond standard model physics. There are also questions about the possible phases of matter created in high-energy collisions. In particle accelerators, matter can be heated to trillions of degrees, recreating conditions milliseconds after the Big Bang. The quark-gluon plasma observed in these experiments behaves as a nearly perfect fluid with extremely low viscosity. Although this state has been observed, its full range of behavior, stability, and transitions remain topics of active research. It remains unclear whether entirely new phases might emerge at even higher energies, possibly the kinds of energies found only near black hole mergers or in the earliest moments of the universe. The existence of these hypothetical states raises deep questions about what matter fundamentally is. If the identity of matter changes under pressure, heat, or density, if it can rearrange itself into forms unrecognizable compared with atoms and molecules, then the concept of ordinary matter becomes just one chapter in a vast story. What we experience daily is only one expression of a much richer spectrum. As scientific instruments improve, we may uncover indirect signs of these states. Gravitational wave detectors might reveal differences in compact object collisions that signal exotic matter. X-ray observatories might detect cooling curves that cannot be explained without new phases. Cosmological surveys might detect structures or fluctuations indicative of unusual field behavior. Each of these possibilities suggests that the universe could still surprise us. And perhaps as you reflect on these ideas, a quiet thought emerges that for all our accumulated knowledge, we still stand at the edge of what is possible. The universe remains larger than imagination, filled with forms of matter and behavior that exceed our familiar experience. Just as star cores revealed electron and neutron degeneracy, and neutron stars hinted at quark matter, the cosmos may hold states not yet named or conceived. In that realization, there is something gently humbling. You are made of matter in its mildest form, atoms arranged at low density, living far from the extremes. Yet the universe allows matter to become almost anything under the right conditions. A quantum fluid, a crystalline lattice of nuclei, a sea of quarks, or something stranger still. Perhaps it is enough to rest with the knowledge that the story is unfinished, that discovery continues, and that even amid the unknown, the laws that govern everything remain steady, quiet, and profoundly consistent. My friend, if you're somehow still awake, there's another journey waiting for you, just a gentle tap away. And if your eyes are already closing, then rest. Let the stars hold you. Let the universe breathe around you, and have the sweetest dreams among the galaxies.